Hi there, it's Paul Bamberg back again with a discussion of how to use the Bernoulli and binomial distributions in R and how the binomial distribution is related to the normal distribution. This assumes that you have watched the video for script 1 and are a little bit familiar with R. Let me start out with a so-called Bernoulli distribution. And to do that, I'm going to try to simulate the behavior of a baseball player who bats .300. That is, one who has a 30% chance of getting a hit every time he comes to the plate. To get started, I'm going to build a vector of 10 strings in R using the concatenate function, abbreviated C, and the repeat function, abbreviated REP. So what I'm going to do is repeat hit 3 times, then repeat out 7 times, put them together, store it in the variable at bats, and then print out at bats, which looks like this. 3 hits followed by 7 outs. Now we can sample from that. If I ask for a sample of 1 from at bats, well, my first try I got an out, second time I got an out, third time I got an out. Just to show that I can get a hit sooner or later, I'll back up, run those lines again. Yeah, we're in a real slump here. There we go. So sometimes you get out, sometimes you get hit, and the probability of getting hit is 30% because there are 3 hits and 7 outs. Now, using this distribution, we can draw larger samples. To simulate an entire game, for example, we could sample 4 times from at-bats. Got 4 outs. Got 4 outs. Got 4 outs. But hits are possible. Now, you'll notice it said at bats, 4. That gives us 4 samples. Replace equals true means that each sample is independent of the others. We're not merely scrambling the 10 symbols, but we're selecting independently from them. And you can see that if I draw a sample of 10, this sample of 10 includes 2 hits and 8 outs. Here's another one that happens to include 3 hits and 7 outs. If I set replace equal to false rather than true, then I do what's called sampling without replacement. I'm guaranteed to get 3 hits and 7 outs. They just come up in a new order. Well, why stop at 10? If we draw a sample of 500, we can simulate a complete season. And if I take the average, I will get the batting average for that season. Let me explain why this works, though. X equals hit, using a double equal sign, is, in the opinion of R, equal to 1 if X is hit and 0 if it's out. And if I take the average of those 1s and 0s, on the average 30% of them are going to be 1s, so I should get something pretty close to 0.300. I got 0.274. Try it again. I get exactly 0.3. Try it again. I get 0.306. And that's what happens with real baseball players. Even if their overall capabilities don't change, they have different batting averages in different seasons. These batting averages are said to have a sampling distribution that's based on the Bernoulli distribution that governs a single at-bat. And the sampling distribution has a name that you probably know. It's called the binomial distribution. Just as what we got for the season was the sum of 500 individual at-bats, you can say binomial random variable more generally is the sum of n Bernoulli random variables, and each of these has a probability p of success. The first argument for the binomial function is the number of samples that we want, and then the second and third arguments control the Bernoulli distribution. The second argument tells us how many trials we have, how many Bernoulli trials we're adding together. And the third one is not really the number of successes, it's the probability of success. So let's try this. This is going to give us one sample drawn from a binomial distribution with one trial and a 30% chance of success. We got a 1. There was a 30% chance of that happening. We got a 0 on the next try, 70% chance of that happening, and so on. Now if we want to get the number of hits in a single game, we have two possibilities. First, as we did before, we can ask for 4 samples from a binomial distribution and then add together the numbers in that sample. That's what sum of x does. It adds together the 4 zeros to get a 0. It adds together 3 zeros and a 1 to get 1. It adds together the 2 1s to get a 2, and so on. But a simpler way of doing this is asking for a single sample drawn from a binomial distribution with 4 trials and a 30% chance of success. Now we don't see the individual at-bats, as it were. We just see the total number of hits. It's 2 one day, it's 1 the next, it's 2 the next day. And we can do the same thing with a larger number of trials, simulating an entire season. We can either ask for 500 samples from the binomial distribution and then take their average to get the batting average for the season, which will vary from one season to the next. Or alternatively, we can ask for a single sample from a binomial distribution with 500 trials, each having a 30% chance of success, and we divide the result, the number of hits, by 500 to get the batting average for a whole season. In doing this, we lose the day-to-day detail that was stored in that vector x of 500 ones and zeros, but we get the same results for the whole season. Now we can do both things at once. We can ask for the sum of our 500 at-bats and store it in the ith component of a vector hits, which was initialized to numeric parentheses n, just to give it 15 open slots into which we can put numbers. And when we do that, we get a record of 15 different seasons, the number of hits in each season. We expect, of course, the average number of hits per season to be close to 150, and it's 147.6, fairly close. I believe you know the formula for the variance of a binomial distribution. It's the number of hits, 150, multiplied by 1 minus the probability of getting a hit. So it's 150 times 0.7. I can also calculate that variance from the samples. I can take the mean of hits squared and subtract off the square of the mean of hits. And sure enough, I get something fairly close to 105. With only 15 seasons, I'm not surprised not to be closer than that. Alternatively, I can display the results graphically. There's a bar plot of the number of hits. Here's a bar plot of a table based on the number of hits. And if you look at this bar plot, you'll see it's subtly different from a histogram. Notice that 126 and 138, which differ by 12, are spaced the same amount as 144 and 149, which differ only by 5. This is not trying to space the numbers uniformly out along the horizontal axis. In order to do that, I need a histogram, which lumps things together so that each span of 10 hits is equally spaced. I've got a fast computer. I can do the same thing for 10,000 seasons. So let's do that. And this time, because I've had lots and lots of seasons, my expectation that the average number of hits will be close to 150 is a very good prediction. And in fact, if I calculate the variance from this sample, it's quite close to 105. I can display the results graphically in a bar plot, which looks kind of like a histogram. It looks awfully much like the histogram, doesn't it? Because every single value for the number of hits between 120 and 180 showed up, and that spaced out the bar plot uniformly. By setting prob equals true there, I have displayed something that can be compared with probabilities. So let's try that. It took me a while to figure out exactly how to overlay the distribution for the binomial, the density function for the binomial distribution on this plot. Remember, dnorm gave us a plot of probability density for the normal distribution. Dbinom gives us the same thing, but it's not a function of a real variable x. It's a function that's only defined for the number of hits that are possibilities, namely 0 through 500 inclusive. So what I ask R to do is plot horizontally the number of hits between 0 and 500, to plot vertically the probability of getting that number of hits, to do it in red, and to represent the number by a red vertical line, which will look like this. And you notice that is surprisingly close in appearance to what we got from our samples. What's more remarkable is that I can overlay on that a normal distribution with the same mean, 150, the same variance, 105. I'm actually supposed to specify the square root, which is the standard deviation. I'll do that in blue, and you see the normal and binomial distributions agree very closely. This turns out to be a fairly universal phenomenon, which will be explored in detail in the next of these videos. Now, if we use our binom, we can simulate our 10,000 seasons without having to do all this tedious sampling. I just ask for a histogram of what I get when I draw n samples. I'd set n equal to 10,000 a while back. And I get a histogram on my first try. Overlay this points plot of the density function for the binomial distribution. Overlay the normal distribution with the right mean and standard deviation. Everything matches up. Given this density function, I can calculate the expected number of hits and the variance. To get the expected number of hits, look at this fairly closely, I take the probability of getting any number of hits between 0 and 500. I multiply that by the number of hits, and then I add up all the results. When I do that, I get exactly 150. If I do the same thing with the square of the number of hits and then subtract off 150 squared, I get exactly 105. When you do computations with probability distribution functions, you get exactly the result you expect. When you do calculations involving samples drawn from that distribution, even with a very large number of samples, you don't get perfect agreement. Let's try with 10,000. There's a vector with 10,000 numbers of hits for each of 10,000 seasons. The average is close to 150. The variance is close to 105, but the matchup isn't perfect. Next to these functions is p-binom. This gives the probability of getting m or fewer successes. So let's look at what happens with our binomial distribution with 4 trials. D-binom is the probability of getting exactly 0 hits. P-binom is the probability of getting 0 or fewer hits. That's exactly the same. D-binom is the probability of getting exactly 1 hit. P-binom is the probability of getting either 0 hits or 1 hit, which is the sum of the 2 results above. D-binom for 4 is the probability of getting exactly 4 hits, unlikely event, the probability of 0.008. P-binom is the probability of getting 4 or fewer hits. That's guaranteed to happen, and the probability is 1. If we do the same thing for a season of 500 at-bats, we can calculate either the probability of getting exactly 140 hits, or the much larger probability of getting 140 or fewer hits. If I want the probability of more than 140 hits, I have to subtract that number above from 1, but I can have R do that by providing the final argument lower dot tail equals false. If I want the probability of between 140 and 160 hits, what I do is calculate the probability of 160 or fewer hits, and then subtract off the probability of 139 or fewer, leaving only the cases 140 through 160 inclusive. Alternatively, I can ask for the probability of getting exactly each number of hits from 140 through 160, add those all up, getting exactly the same number. As a final topic, I'm going to show you how to estimate binomial probabilities by using a normal distribution. As you've seen, the distribution numbers look very, very similar for large values of n. So here is a plot of the binomial distribution function for values of 0 up through 500. The probability of getting fewer than n hits is quite small until we get up close to 150. Then it rises very rapidly until once we have a number significantly larger than 150, the probability of having fewer than that number of hits is very close to 1. I can compare that with the corresponding result for the normal distribution, and the two match up very nicely. We can look at the matchup more closely if we just focus our attention on values between 120 and 180. There's the result for the binomial distribution, where you'll notice only an integer number of hits can occur, and the corresponding result for a normal distribution. Now, if you look at this, though, you'll say, looks to me as though that red curve is a little bit below all the black and white circles. We'll fix that in a minute. First, let's try doing the same thing with the density function. There's a plot of the density function for the binomial distribution between 120 and 180. Here is a plot of the normal distribution, and it matches up beautifully. If you're doing this on your own, you want to remember to use this type equals h in order to get vertical lines out of your binomial distribution. Now, back in the pre-computer era, people carried around tables of the standard normal distribution. Basically, armed with such a table, a statistician who was willing to do a little bit of arithmetic could work out things for any normal distribution. However, to do the same thing for the binomial distribution, you'd have to carry tables for 500, for 501, for 502, an unacceptably large number of tables. So it was very useful to be able to approximate binomial distributions by normal distributions. How do we do that? Well, if we've got n trials and a probability p of success, as I believe you know, the expected number of successes is n times p, and the variance is n times p times 1 minus p. If you are trying to simulate m or fewer trials with a binomial distribution, it's a good idea to ask for the probability of getting up to m plus a half with a normal distribution, thereby including a full range of width 1 around the highest number that you're considering. Let's try this and see how well it works. P binom for 140, 500 trials, probability of success 0.3. That's the probability of 140 or fewer hits, 0.177. I ask for the probability that a normal distribution with an expectation of 150 and a standard deviation of 150 times 0.7. I ask for the probability that that's less than 140.5, and I get almost exactly the same number. I can compute exactly the probability of getting between 140 and 160 hits, and if I cleverly ask for the probability that a normal distribution will give me a number between 139.5 and 160.5, again, I get almost perfect agreement. Given the availability of this p binom function, it's not clear that anyone needs to do this anymore, but it's still nice to know that it works. And with that, I bring this video to a conclusion.